It's my honor now to introduce your next speaker. The next speaker is Professor Don Page. He's a professor of physics at the University of Alberta. He's worked on quantum theory, cosmology, and black hole physics. In particular, he has collaborated with Stephen Hawking on the thermodynamics of black holes. And he has also helped create the renowned Page-Wootters model, a model in which time is not a fundamental concept, but emerges from entanglement in quantum systems. So Professor Page, please, the floor is yours, and we're really happy to have you on this conference.
Well, thank you very much for organizing. It's really great to have this Zoom conference. I wish I could meet all of you in person, but at least it's good to see faces of you and other people, or friends, and so on. So yeah, I'm going to talk. My slide here is of Moraine Lake, which is in the Canadian Rockies, and the Valley of the Ten Peaks is from the top of Mount Temple, which is kind of the highest mountain near that area. So I'm going to talk about preferred operators instead of preferred basis states. Now let's see, go down. So Everett showed that one need not have wave function collapse in quantum theory. Instead, one can have a single quantum state in the Heisenberg picture that never changes. However, if one decomposes the state into basis states, there would generically be non-zero amplitudes for many different basis states, sometimes called Everett many worlds. And many have sought to answer the challenge of finding a preferred set of basis states in order to get a preferred set of Everett worlds. So I'm arguing that the search for a preferred basis states, at least for the whole universe, is misguided. And what we need instead is a set of preferred positive operators. So these would be the operators whose expectation values I propose would give the relative measures for observations. Now, I should say, I do find there's an awful lot valuable in the decoherence program, but I don't think it necessarily gives you a unique preferred basis for the whole universe. I mean, maybe it can for some subsystems and so on, and it'd be interesting to see how maybe it can be helpful for finding these operators that are useful for observation. But I'm saying, well, it's a more important problem is to find the operators whose expectation values give the relative measures for observations. That's more important than finding some basis of the quantum states. So, okay, in my view, a complete theory of the universe would not only give the complete set of dynamical laws, what's been, at least often by particle physics, misleadingly called a, quote, theory of everything, but also the quantum state of the universe, such as what Hartle and Hawking have proposed, and Vilenkin and other ones. That's still not, there are still problems, technical problems with some of the particular proposals. And thirdly, the so far unknown rules for extracting the probabilities of observations from the quantum states. So I shall propose a basic framework for these rules, that the measure for each observation be the expectation value in the quantum state of the universe of a corresponding positive quantum operator for each possible observation, which I shall call an awareness operator. Now, one needs to say what observations are, and I propose that most basically they're sentient experiences or conscious perceptions, like it all, each being the entirety of a conscious awareness, all that one's consciously aware of at once. Then I shall explain why, for a large universe with indistinguishable copies of observers, the quantum awareness operators cannot be projection operators, as one might have assumed from Born's rule. So I'm saying Born's rule does not work for giving probabilities of observations. Okay, now to introduce, I would say that bare quantum theory describes the universe in terms of quantum states, operators, expectation values, wave functions, amplitudes, path integrals, etc., but does not by itself connect these to observations. So bare quantum theory is not directly testable. Well, to make comparison with observations, Max Born suggested that the wave function gives probabilities. Later it was proposed that probabilities are given by the absolute squares of amplitudes, and these can be taken to be expectation values of projection operators. So in this, well, I should change paper to talk. In this talk, I shall take the mathematization of Born's rule to be the idea that the probabilities of observations are given by the expectation value of projection operators. And then I'll show that doesn't work and propose alternatives. So now I like to do a Bayesian analysis for theories. So consider a theories T sub I, that for each possible observation, O sub K, they each give a probability for the observer, probability of O sub K given T sub I. So that's the conditional probability. If the theory were correct, what's the probability it gives for the observation? Then if to get posterior probabilities for the theory, it seems that we do need to assign prior probabilities P sub Ti to the theories T sub I. As far as I can see, these are subjective, though in science we generally adopt Occam's razor of favoring simpler theories and giving simpler theories higher prior probabilities. Then we use the observation to test the theory, P of O given T. It's then what's called the likelihood of the theory. And by Bayes' theorem, we can calculate the posterior probability of the theory as the product of the prior probability of the theory times the probability of the observation given the theory, and then normalize that by dividing that by the sum over all possible theories. So we would like to get the posterior probability as high as possible by choosing a simple theory, which if we adopt Occam's razor would have high prior probability, and that gives a good statistical fit to one's observation, O sub K, so high likelihood. So there's the two factors in there, and there's a trade-off often. So now there's the question in a complete theory, what are these observational probabilities? Since a complete theory for a universe should completely specify all properties of that universe, one might think it has no room for probabilities between 0 and 1. So all likelihoods PO sub given T sub I would be 0 or 1. I might say as an aside, collapse theories of quantum theory, in my regard, they would not be complete until they specify exactly what collapse actually does occur. So whereas Everett's, you don't have the collapse, so you don't have to, you don't have to specify what the collapses are because there just aren't any collapses. And I'm taking the Everett view of no collapses. Okay, then if you did say that all the likelihoods are 0, 1, then the posterior probabilities of these theories, given the observation, would just be proportional to the prior probabilities of theories that do give this unit probability for that. So they would, so except for just excluding theories that don't predict that the observation occurs, all the posterior probability would just be given by the prior. So it would be sort of completely theory, no real impact for observations, except this minor one of excluding theories that don't predict that the observation exists at all. So for observations to play a bigger role in science, which as a theorist, I admit that the experimental physics and the observational sciences are very important. And so we would like to get a way of getting likelihoods between 0 and 1. Now, suppose the theory can give normalizable measures for the observations, even if all observations occur, but if they all have measures and they're normalizable, then the normalized measures I'm proposing can be interpreted as if there are these likelihoods, P of O sub K given T sub I, that can vary between 0 and 1. They're not really probabilities in the sense that they're not propensities for potentialities to become actualities. They're really actual measures of the observations that are determined by the theory. But if they can be between 0 and 1, then I'm proposing that they could be used in a Bayesian analysis as if they were probabilities. I mean, they would be in the hypothetical thing where you imagine somebody outside the universe picking an observation at random and using this measure as the weight for that. Then you could say if an observation were picked at random by some outside, then that would be a probability in the more traditional sense. But I'm not proposing, I'm proposing they all do exist, that there's nothing that picks them out. All of them with positive measure do occur, but with different measures. Okay, now what could these measures be? In a classical theory, the measures could be functionals of the phase space trajectory, such as the times that the system spends in different regions of the phase space. You can imagine one region corresponds to one observation, another region corresponds to another, and so on and so on. And then the trajectory passes through all this, and then you could see the the times that they spend in there could be the relative measures, and then if you could normalize it, you could interpret them as if they're probabilities. Now, in quantum theory, the measures could be certain functionals of the quantum states, or maps from the quantum state to non-negative numbers. So here's another argument against all likelihoods 0 or 1. If a specific theory leads to the definite existence of more than one observation, one might be tempted to say that the probability of the observation given the theory is 1, because it definitely occurred. And for all of these observations, that would give unit likelihood for any theory predicting the definite existence of the particular observation used to test the theory. But then this procedure would mean you can construct a theory of maximum likelihood, namely unit likelihood, no matter what the observation turns out to be, just by having the theory predict that all possible observations definitely exist. But this seems too cheap. It's supposedly explaining everything. It says everything has unit probability, therefore it's unit probability that your observation occurred, but it's not distinguishing yours from, I mean, it's really explaining nothing. And that's indeed, some restricted, some complaints about multiverse theories are of this nature. And I think even a true multiverse theory should not predict all possible observations with equal measure. So I'm proposing the normalization principle, or you might say meta theory, that each theory T sub I gives normalized probabilities for the different possible observations. So for each theory, the sum of the probabilities of the observation for that theory is unity. Well, it's just the usual thing that you want the probabilities to add up to unity, and this is conditional probability, so conditional on the theory, the probability of the observations should add up to 1. So, okay, there's this trade-off between prior probabilities and likelihoods. The prior probabilities, P sub Ti for the theories, those are intrinsic plausibilities for the theory before you consider any observations. Of course, they're very hard for humans to take because our existence is conditioned on things. So it's pretty hard for us to really be that. And as I say, that seems to be subjective. I don't know of any way that you could deduce that, from something. But if you apply Occam's razor, you might say simpler theories give higher. But even if you could order the theories, there's still a question of how much weight to give to each theory and so on. Okay, then there are these conditional probabilities for observations, or the likelihoods for the theory with a fixed observation. And then the posterior probabilities are proportional to the product. So prior probabilities are subjective, usually higher for simpler theories. And the highest prior probability might be for the theory that nothing concrete or contingent exists, that only mathematical truths or just pure logic exists, but abstract, but nothing concrete. But then since observations I regard as concrete, the probability of that would be 0. So the posterior probability of that theory would be 0. Then maybe the next simplest theory might be the theory that all observations exist equally, but then surely there's an infinite number of possible observations. So then if all exist equally, the likelihood of any particular one would be 1 over infinity, would be 0 when you normalize. So this would be my criticism of theories like David Lewis, although he didn't put a measure on it, but he said that basically anything logically possible actually occurs. Maybe there's all these different worlds where, well, different, I don't know what you call it, because the world's supposed to be everything in the philosophical thing. But anyway, he didn't really put. But if you just said all of these different things have equal measure, then the likelihood would be 0. So that would be the way I would rule out something like David Lewis's modal realism theory. If you augment it by putting measures on these theories and saying, or on these different possibilities and saying that they're uniform. Now the other extreme would be a maximum likelihood theory, giving the probability of unity for one's observation. And of course, if that's normalized, it means you're giving 0 probability for any other observation. So that would be sort of like an extreme solipsistic view, not only that do only I exist with my observation, but only my present observation. And anything in my memory, I mean, anything I'm aware of now of my memory would be part of my present observation. But these memories would not be really referring to any previous observation that would dilute the measure. So this would be a maximum likelihood theory. So, but this seems to require a very complex theory. If you had a complex theory that just produced one observation and no others. And so although it's a bit subjective, I think that because it's complicated, I think it'd be very plausible to assign this an extremely tiny prior probability. And so you'd get even though the likelihood is maximum, it's unity, you'd still get a very low posterior probability. So I think there's this trade-off between prior probabilities and likelihoods, between intrinsic plausibility and fit to observations. So now let's relate a little bit to cosmology. The measure problem of cosmology is how to obtain probabilities of observations from the quantum state of the universe. And this is particularly a problem when internal inflation leads to a universe of unbounded size, so that there are apparently infinitely many realizations or occurrences of observations of each of many different kinds of or types, making the ratios ambiguous. And there's also the danger of domination by Boltzmann brains, observers produced by thermal and or vacuum fluctuations. So it seems this measure problem is related to the measurement problem of quantum theory, how to relate quantum reality to our observations that appear to be much more classical. So I'll take this approach that observations are fundamentally conscious perceptions or sentient experiences, each being the all at once consciously aware of at once. So I shall take an Everettian view that the wave function never collapses. So in the Heisenberg picture, there's a single fixed quantum state for the universe, which could be a multiverse. And we could have many different parts with different coupling constants and so on, but it's all a single quantum state. And I shall assume instead of many worlds, there are instead many different actually existing observations, many different sentient experiences, yours, mine, people in the past, people in the future, people in other branches of the wave function, perhaps people in other branches of the multiverse where there may be different coupling constants if that allows consciousness and so on. So there's many of these, but they have different positive measures, mu sub k. It's the measure of this observation, which are in some sense how much the various observations occur, but these measures are not determined by just the contents of the observation. And for simplicity, I shall assume that there's a countable discrete set, O sub k, of observations, and that the total measure is normalized to unity for each possible complete theory that gives the normalized measures mu sub k for all possible observations. So then in a Bayesian analysis, I shall interpret the normalized measures of the observation that each theory gives as the probability of the observation given the theory, even though it's not really probability in the sense that there's any randomness or uncertainty or indefiniteness. Well, there's uncertainty for individual observations within the universe, but from a view of the whole, if you could view the whole quantum state, there would be no uncertainty about it. But I'm interpreting as if there are these probabilities, these likelihoods that you can put into the Bayesian analysis. So now I have a particular framework for this I call it sensible quantum mechanics, or in the popular thing I wrote called mindless sensationalism. So the map from the quantum state to the measures of observations could be nonlinear. I mean, an example of a nonlinear thing is when in decohering histories, you have sets of histories that are decoherent. Those sets depend non-linearly upon the quantum state, and so then the measures for these sets or for each element of the set, or the probability of a particular history within a set, then of course depends on the set, which depends on the quantum state in a non-linear way. However, in my mind, it's somewhat simpler to assume a linear relationship. There's no way for me to prove that that's right, but I'm assuming a linear relationship in the sensible quantum mechanics. And I've also found the sensationalism because it proposes that what's fundamental is not minds, but conscious perceptions, which crudely might be called sensations, although they include more than what one is consciously aware of, e.g. memories, and usually called sensations. So that's a little bit of a misnomer to say it's just sensations, but I am staking what's fundamental are the individual conscious perceptions and not any unique sequences, because the sequences, might effectively split, if you've in everything. Okay, so the measure, this mu of this observation, I'm proposing is the expectation value of a corresponding operator, A of O. I'll call that A sub k. That's a positive operator. And this sigma denotes the quantum state, which is a positive linear functional of quantum operators. So, okay, so the measure is the expectation value of this awareness operator, or the expectation value of that, or I could say it's of A sub k, which is the same as A of O sub k. So sigma is the quantum state of the universe, a positive linear functional of quantum operators, and A sub k is a non-negative, what I call an awareness operator corresponding to the observation or sentient experience, or consciousness perceptions, another phrase I use synonymously, O sub k. And the quantum state could be a pure state, it could be a mixed state given by density matrix, or it could be a C-star algebra state. I'm being agnostic as to what the quantum state of the universe is. And the awareness operators, along with this linear relationship above, and also complete description of what the observation is, they're all supposed to be given by the theory. So complete theory, in my mind, if it has this form, it will have these elements. So now let me talk about Born's rule. Traditional quantum theory uses Born's rule with the probability of observation being the expectation value of an operator that's a projection operator. So applying it twice, you get the same one back. If you've applied the same one twice, if you apply two different orthonormal projection operators, after that you get 0. And so in that case, the probability of the observation would be the expectation value of a projection operator. So Born's rule works when one knows where the observer is within the quantum state, e.g. in the quantum state of a single laboratory rather than the universe, so that one has definite orthonormal projection operators. However, Born's rule does not work in a universe large enough that there may be identical copies of the observer at different locations, since then the observer does not know uniquely the location or what the projection operators are. So let's spell this out a little bit. Why does the Born rule die? Suppose there's two identical copies of the observer at locations B and C that each can make the observation O sub 1 and O sub 2. And let's suppose these observations do not reveal the location. They don't show whether you're at B or C. So Born's rule would give a probability P sub 1b is the expectation value of this projection operator at location B, and P sub b2 for the projection operator to the other observation, if the observer knew that it were at location B, with the projection operators there being P super B for the location and sub 1 for the first observation, and P super B and sub 2. Similarly, I give the probabilities P superscript C for the different location, the expectation value of that projection operator, and P sub T2 for the other operation at the location C, if the observer knew it were at location C with the projection operators being there. However, if the observer is not certain to be at B or C, and without loss of generality, let's suppose that the probability of the observation 1 at location B is less than the probability than this projection operator expectation value at C. If you're uncertain, then the probability should be between these two. But there's no state-independent projection operator that gives an expectation value with this property for all possible quantum states. So if you're, if the projection operator is supposed to be chosen before you imagine applying it to different quantum states, then you can't get that. So no matter what the orthonormal projection operators P sub 1, P sub 2 are, there's an open set of states that give expectation values that are not positively weighted means of the observational probabilities at the two locations. So the Born rule fails in a cosmology when it's large enough to have two observers that can't tell where they are. There are two copies at two different locations, and their observations don't tell them which of the observations they are. So, okay, so let's see, just a second, yeah. So the failure of the Born rule means that in a theory T sub I, these awareness operators whose expectation values in the quantum state sigma sub I, the I telling which theory of the universe, it gives the probabilities of normalized measures for the observations as probability of observation given T sub I. It's the measure of that O sub I, and that's the expectation value of the operator A sub I of O sub k. In other words, the expectation value of the awareness operator in that theory. So they cannot be projection operators. However, the awareness operators could be weighted sums or integrals over space-time of localized projection operators, P of O sub k comma x, at locations denoted schematically by x. That can include the location and time also. Say onto brane states there. So suppose you have a localized projection operator onto some region of space-time onto what would be a brane state at that location. That's what it could be, and then you would weight these integrate over the space-time. Now, this does lead to a problem, because in the Boltzmann brane problem, in local quantum field theory with definite globally hyperbolic space-time, any positive localized operator that's localized to be just act non-trivially within some finite region, such as a localized projection operator, will have a strictly positive expectation value in any non-pathological quantum state. So there's always some probability of finding, some non-zero probability of finding something just within this small region. So for example, the charge, you can find the charge positive. There's always some probability to find positive charge within a finite region. Of course, if you go all the way out to infinity, you can have a state with zero that charge, and the probability is then zero of finding the total charge of the whole universe to be positive. But for any small region, the probability of the expectation value of a projection operator onto non-zero charge in this finite region could be positive, and similarly for any other projection operators. So if such a prediction localized operator is integrated with uniform weight over a space-time with infinite Fourier volume, it will give an awareness operator with an infinite expectation value. So you won't be able to normalize it. Now you could say, let's cut it off. If we take the integral only up to finite cutoff time t sub c and normalize the resulting awareness operators, then for a universe that continues forever with a 3-volume bounded below by a positive value, the integrals will be dominated by times of the same order of magnitude as the cutoff time. If at late times the probability per Fourier volume drops very low for ordinary observers, that is ones that that arose from stars and planets and evolved like we did, if they just come from these expectation values in something that's near the vacuum, then most of the measure for observations will be contributed by thermal or vacuum fluctuations, so-called Boltzmann branes. That is, Boltzmann branes will dominate the measure for observations. So if Boltzmann branes dominate the measure for observations, one might say, so what? Couldn't it just be that our observations are that of ordinary observers? Or couldn't it be that our observations really are Boltzmann branes that happen to have the ordered observations? But in this Bayesian analysis, that doesn't work. Since Boltzmann brane observations are produced mainly by thermal or vacuum fluctuations, it would be expected that only a very tiny fraction of their measure would be for observations so ordered as our observations. This tiny fraction, plus the even smaller fraction of ordered observer observations in comparison with the dominant disordered Boltzmann brane observations, if you put the cutoff far beyond the lifetime of stars, say, then way beyond, sufficiently far beyond that these Boltzmann branes dominated, then the ordered observations would be only a tiny fraction of the measure of all observations. So thus the normalized probability of one of the ordered observations, which we use as the likelihood of the theory, if we're taking one of our ordered observations to test the theory, then that would be highly diluted, and it would be much smaller than those of alternative theories in which Boltzmann branes do not dominate. So if these alternative theories do not have prior probabilities that are too small, they would dominate the posterior probabilities. In other words, you might need to complicate the theory a little bit to get rid of Boltzmann branes, but if you don't do that, then the likelihood of our order observation will be extremely low in the Boltzmann brane theory, and so it would get a low posterior probability. So in summary, Boltzmann brane domination, which is predicted by many simple extensions of current theories, e.g. with the awareness operators or their equivalent being obtained by uniform integration over space-time up to a cutoff that's then taken to infinity. this gives a reductio ad absurdum for such theories. It makes their likelihoods very small. So surely there are alternative theories that avoid Boltzmann brain domination without such a cost of complexity that their prior probabilities would be decreased so much as the gain in likelihoods for not having the normalized probabilities of our ordered observations highly diluted by disordered brain observations. So I view that this Boltzmann brain problem is analogous to the ultraviolet catastrophe of the late 19th century classical physics. Physicists then did not believe that an ideal black body in thermal equilibrium would really emit infinite power, and most physicists now do not believe that Boltzmann brain really dominate observations, but it's a question of how to get rid of them. And there may be some cost of complexity, but I'm arguing that surely there must be some way of getting rid of them, that the cost is not as much as the gain in likelihoods. So, okay, so I've made some partial attempts on this. These are all sort of schematic, and also they're not terribly elegant. So although I think they add less complexity than I think they would definitely increase the posterior probabilities, but they might be increased more by finding more elegant solutions. So the approach that gives awareness operators of universe integrals over space-time and localized projection operators, or equivalently, many people don't talk about these operators. They just count all observation occurrences equally, no matter when and where they occur in space-time. That gives it an especially severe Boltzmann brain problem in space-times with a positive cosmological constant, as ours seems to have, with the spatial hypersurfaces having 3 volumes that asymptotically grow exponentially, as in the k equals 1, or in other words, closed 3-sphere slicing of the de Sitter spacetime. At each time, counting the number or measure of observations as growing with the volume is called volume weighting. Well, in 2008, I proposed the alternative of volume averaging, which gives a contribution to the measure for an observation from a hypersurface that's proportional to the spatial density of the occurrences of the observation on the hypersurface. So that would be rewarding the spatial frequency of observation occurrences rather than the total number that would diverge in eternal inflation as the hypersurface volume is taken to infinity. So it would say the spatial density is surely much higher now when we have stars and planets and ordinary observers. The Boltzmann brain thing, I mean, the probability per 4 volume may be very low, e to the minus 10 to the 42 or something. It could be exponentially tiny, but the problem is it's not 0. And so if you go to infinite volumes, it diverges. Okay, now this volume average ameliorates the Boltzmann brain problem by not giving more weight to individual spatial hypersurfaces at very late times when Boltzmann brains might be expected to dominate. But you still have to consider integrate over all the time over the sequence of hypersurfaces. And if you do that with it, measure uniform in the element of proper time, you get to linear divergence if the time goes to infinity, because at very late times, the density of Boltzmann brains just goes to a constant. So you need some suppression at late times to meet this divergence. So in 2010, I proposed Agnesi weighting, which admittedly is ad hoc, but I replaced dt by dt over 1 plus t squared, where t is measured in Planck units, which of course the integral of that converges. Of course, you see it's ad hoc, but it's a simple function that the integral converges. So if you had weight, the weight would go down with time. And more recently, I proposed new measures depending on the space-time average density, or SAD, of observation occurrences within a proper time from the Big Bang or bounce. And when these measures are combined with volume averaging and a suitable quantum state, such as my symmetric bounce one that I won't have time to talk about here, but that has the universe having a bounce when it was really small, they appear to be statistically consistent with all observations and seem to give much higher likelihoods than current measures using the extreme view that the measure is just given by the quantum state. So now there may be other questions that we can try to hope to be answered once we find more about these awareness operators. And that's, why do we not observe ourselves to be ants? Other observations that at least naively seem difficult to explain by Born's rule include our observation there were humans rather than ants, despite the much greater number of ants on Earth. So if you said it was proportional to projection operators onto some sort of sentient being, and let's allow that ants could be sentient. If you just have simple projection operators, then the ant might count for just about as much as a human. Well, there may be more, there may be a certain number of more projection operators just because of the bigger size of humans, but anyway, it might be more comparable if if the probabilities were just given by projection operators. So, but there's ways the modifications of Born's rule can explain the probabilities of observations by the way that it can explain by copies, the fact that we apparently do not observe ourselves to be bolts and brains, and by modifying it so that from the Born rule, we can also explain the fact that we do not observe ourselves to be ants. However, it's not yet known what the correct modifications are, so there's many possibilities for probabilities of observations. So I have a framework, but I don't have a detailed theory because I don't have a detailed theory of what the awareness operators are. So here, I'll not give an exhaustive list of possible replacements for Born rule, but just describe a few of the basic possibilities. The simplest set of possibilities seem that the probabilities of observations are given by the expectation values of positive operators, a sub I, each one for each observation, that are not projection operators, as I've discussed. And then if angular brackets denote the expectation value of an operator, then the probability of the observation is given by this expectation. And here I will assume we haven't necessarily normalized the operator, the a sub k, so that maybe the expectation values, some of them for all AKs, they may depend on the theory, that may depend on the quantum state. So here I'll allow that, but then I'll just normalize it. So the probability of the observation in a particular theory is just the normalized expectation value of the awareness operator. So then the main open questions in this sensible quantum mechanics framework, in which the probabilities of observation or the expectation values of positive awareness operators, one for each observation, is what these awareness operators are. So this SQM framework does not assume that there's a space-time, so it would be valid even in formulations of quantum gravity in which space-time is not fundamental. However, if the part of the quantum state that gives the dominant contribution to the expectation value of the awareness operators can lead to the approximation of an effective space-time or of a quantum superposition of space-times, one idea is that the contribution to the expectation value of an awareness operator from each space-time in the superposition is the expectation value of the existence of this space-time multiplied by the weighted sum or integral over the space-time of a localized projection operator for each space-time region. So here I'm ignoring possible interference between different spacetimes, but assuming that there's some quasi-classical spacetime, there's a whole set of them with expectation values, and then in each one we do an integral over them. And then to avoid both and brain, we'd have to do this integral in a way to avoid things. Let's see, I think I'll skip over that, but I kind of said most of that, but I'm running out of time. And then to explain why you observe ourselves to be humans, despite the greater number of ants, it seems plausible to postulate that humans' brains are much more efficient in producing sentient experiences than ants. So the total probability of human conscious observations is not far below that of ants to make human observations much less probable. So, I mean, the thing is, if the ants dominated, since the total has to add up to 1, it would dilute the human observations. It would make our less probable. Therefore, one might postulate that the localized projection operators for human brain configuration should be given much greater weights, W sub k, than the localized projection operators to ant brains. So it's weighted projection operators, and part of the weight could have to do with the complexity, or something about the human brain. Perhaps some part of this weighting should be the complexity of the corresponding brain, since human brains seem to be much more complex than ant brains. But I am skeptical of the hypothesis that simply getting high complexity or high information processing is by itself sufficient for getting a large weight multiplying the corresponding localized projection operator for corresponding awareness operators. As an example, it's not at all obvious to me that even if you got some computer that is eventually is much more complex than the human brain, that it would necessarily be have more observation, more measure of observations than humans. There may be other particular facets about humans that make their observations have higher weight. And then, it could be that we find ourselves to be humans just because of the selection principle, that we find ourselves to be some of the more probable, some of the systems that give higher measures for awareness operators. So, okay, so a schematic formula, if you suppose that the expectation value of a given space-time is E sub S sub L is a E sub L, and that the space-time, in this space-time, the expectation value of the localized projection operator corresponding observation is in KL. So it's sort of like a number density of the observations in this space-time as a function of space-time. And suppose this space-time, the weight factor for the integration over 4 volume is Wi. It depends on the location. For example, it could be 1 over the volume of a hypersurface at a certain time, and in the denominator multiplied by 1 plus t squared. Anyway, so you get some integration factor that converges, and that the intrinsic weight factor for the observation is W sub k. So that would maybe be higher for human observation. Then the relative probability would be, you would have the weight for the observation, Wk. Then you'd have a sum over space-time, so the expectation value of the space-time. And then you'd have an integral over the space-time volume with this volume weighting factor, and then times the density of the expectation value of the localized operator. So that's sort of a schematic form you could have if indeed it's dominated by parts of the wave function where there is space-time. And then, okay, this shows there's a lot of freedom in the modification of Born's rule in cosmology, even within the restriction of sensible quantum mechanics, in which the relative probabilities of the observations are expectation values of the positive operators that are the awareness operators corresponding to the observation. There would be even more freedom if one abandoned this linear relation of SQM and allowed the relative probabilities to be nonlinear in the expectation values, such as these expectation values to a power S that's different from unity, or be even more general functionals. S0 would be sort of just counting the observations, but if S is not too far from 1, it'd be very hard to tell the difference. So if you go beyond sensible quantum mechanics with its linear relation and then goes to this non-linear relation, you might ask how that can be consistent with observations to have S significantly different from unity. The key is to remember the piece of K is the relative probability of an observation itself, which I'm taking the ascending experience. It's not the fraction of results recorded one way rather than another for some unconscious recording device. It would give you, if you observe these results, it would give you the relative probabilities of the observation of the total results or whatever. And so if you had some Gaussian, then the shifting S away from 1 might shift the Gaussian for, what you'd expect to see for the number of heads or tails. But if S is pretty close to unity, then the Gaussian would not have, the spread would be pretty much the same. And so anyway, it's not the frequency of things that are recorded. Okay, so that I think concludes my talk, and I'm grateful. Well, discussions of darn, I should have had a lot of other people. I forgot. I asked the organizers to send me a list of people here. I was going to acknowledge other people I've talked about here, but when I wrote the paper based on this, I just visited Sean Carroll and Caltech. So sorry, I forgot to add in the. There's many of you that I'm grateful for conversations with. Okay, so that'll end my talk.
Thank you very much, Professor Page. I invite everyone with me for a round of applause. Great. So we are good to have some questions. I see a hand rise by Charlie Bennett. If you want to unmute yourself and please ask your question.
Well, I don't think the ant problem is very big. Maybe most of the conscious awareness in the world is by ants, and they don't think there's a people problem because most their people are big and destructive, but don't seem to be thinking very much. And really, I would say the ant problem is a little bit like the problem until recently that the cosmologists seem to be almost entirely male, and it's not because the females don't think. It's just because they weren't cosmologists until recently.
Right. It's just, I guess the ants probably wouldn't dilute I mean, there's so much uncertainty in what this measure is that if the ants had equal, it would dilute it by maybe a factor of 1,000,000. But I mean, I think we're talking about enormous factors in this, in these posterior probabilities. So it's perhaps true that just diluting reducing the likelihood of the theory by a factor of 1,000,000 maybe wouldn't do much. If say if the ants had 1,000,000 times
well, it's just that you should be considering not the total number of ants, but the number of ants that are holding Zoom conferences about cosmology.
Well, I'd rather get a theory that has all possible observations and normalize the measure for all of them, and not. You can, of course, once you've got those, you can of course do conditional probabilities of thoughts of people attending Zoom, where they think they're attending Zoom conferences and so on and so on. But I mean, I would prefer that the theory give basically the probability for an observation itself, and that you could then use that better to test theories. Once you start taking conditional probabilities, it becomes more, it becomes more arbitrary. Which conditional probabilities are you taking? So I'd prefer to just stick with all conscious observations and normalize the total measure for all of them. Your screen looks frozen.
Is there any? Yeah, I see another question from Ding. Ding, if you want to unmute yourself and ask your question.
Yes, thanks. Thanks, Noam, for the nice talk. I just wonder about conscious observations. Do you think it's possible for some conscious being to observe superpositions? And if so, how do you incorporate that into your formalism?
Yeah, I don't know. That is something, I guess, it's curious as to how is this, what properties do these have that normally they don't see that? I mean, decoherence may help with that, but I'm a bit mystified, and maybe I want to ask Wojtek Zurek, or some other thing about the fact that, he talks about they talk about in decoherence that the density matrix of this system that becomes decohered, it becomes diagonal or becomes close to being diagonal in the pointer basis. But if you ask the basis in which it's exactly diagonal, at least in the very simple models of Joost and Day, this density matrix, most of the eigenstates of it have the spread of the original thing. So in other words, if there was a huge spread in the position of, it's very big. So exactly why we don't see a big spread in position, it's not yet completely obvious to me. I hope maybe decoherence can help with that, but I'm trying to learn more to see, does it really help with that?
Should I interject?
Yes.
Yeah,
Well,
no, I think
I want to ask a question, particularly many places you talk about the diagonality of the density matrix as a symptom of decoherence.
yes.
But are you saying that it's a symptom that generally occurs, or are you just saying it can, in some cases it can occur? Because it certainly doesn't seem to occur in the Jose model, where you just have this particle that's moving, say, in one dimension and interacting things. If you calculate the density matrix of that, then the eigenstates of that density matrix, basically each one, if you have a Gaussian and you got the full, the spread, the variance of X is this, all of the eigenstates have the same expectation value of X, say the middle of the thing. And so the variance of the if you average the variance over all the eigenstates, that's just the same as the variance of the original thing, which is very big. So is that?
Yeah, so it sounds to me like an invitation for another talk that I should give, but I won't, right? So let me just keep it to something very quick. So first, coming back to what Ding asked, can you observe superpositions? You do observe superpositions all the time. The point is, if you have a vector in a certain basis, it is superposition in another basis. So if you have states which are sufficiently localized, they are superpositions of momenta, for example, right?
Right.
So, you know, it's not so much do you observe superpositions, you do, because you have complete freedom in adjusting the basis. Now, the point that I think addresses some of what you've asked has to do to some extent with decoherence. So indeed, diagonalization is a symptom which occurs after some time and which is imposed by the interaction Hamiltonian or generally by Schrödinger equation, but you need Hamiltonians to run the Schrödinger equation. But in a way, the real question is not so much what are the states of the systems, but what will you perceive, right? And the business of quantum Darwinism is answering precisely this question. So that means that there are these stable states, and only stable states can get transcribed in many copies on the environment. And the moment you have nonlinearity, and you need nonlinearity to go from one original to many copies, you have to perform selection of what can be copied. So this was, you know, the first part of my talk yesterday, if you still remember. It's a repeatability, right? You need to have something that survives. And, you know, the nice thing that comes out from both decoherence and quantum Darwinism is that the requirement of survival, which is what gives you eventually diagonalization and pointer states, is also the requirement for being able to make multiple copies. So I think these things work together. And I better stop here because I'm gonna run over time.
Let me just ask you about this. I'm a bit bothered by this example. I mean, of course, it's an extremely simple example, and maybe the simplicity of it is what's misleading. But as I understand it, and I did some calculations on that, the use-say model, you have this particle that's moving.
Yes.
I actually extended to a baseball, and which I said that suppose
you mean the dust grains, the dielectric sphere.
Well, it wasn't. I was just using their thing where they had some. They just had some cross section for interactions.
Keep going. Maybe I'll get the context.
But in the very simple model, suppose I imagine. Okay, let me just say it's a baseball as an example. It turns out that the baseball with the Planck momentum has going at 100 miles per hour, which is about the maximum speed that I'm pitching. Anyway, let's suppose that we started with a state that's a minimum uncertainty state at the beginning, but the uncertainty in the momentum, it's got zero expectation value for the momentum, but the RMS value of the momentum is the Planck value. So its RMS value of the velocity is 100 miles per hour, and we'll have a minimum uncertainty. So the position spread, it's a half of a Planck length for the center of mass of this thing. Okay, so it's got big momentum, so it's very, it very rapidly, classically, it very rapidly spreads out. Now it interacts with the environment, and the Yosei thing leads to, if you calculate the density matrix now of this baseball, you get the eigenstates of the density matrix basically have the same form except for some phase thing that oscillates. It's the same as the energy eigenstates of a harmonic oscillator, even though I'm not putting as a harmonic oscillator there.
Sure.
But the basic claim is that each of these eigenstates has zero mean for the position. So the center of each of these eigenstates is at position 0. But then and the grounds, well, the one with the highest probability is indeed sharply peaked about that, but there's an enormous number. I mean, it's like having a temperature much higher than the frequency of a harmonic oscillator. So it's sort of like a thermal state in a harmonic oscillator, but it's not a harmonic oscillator. It's not thermal. So the idea is that most of these eigenstates have a variance that's comparable to what you would get from this 100 miles per hour for however long you take it. So in other words, these states that seem to arise from of course, this is a very simple model, just with the interaction of the environment, it doesn't localize the baseball. I mean, each of the in the basis in which the baseball is density matrix is diagonalized. In that basis, the baseball doesn't get localized. It's got on average, the variance is the same as the full variance. So is that, I don't know, is that, I mean, in other words, and that's a state, I mean, that density matrix is what happens a long time. So it's surviving. Now, I don't know what happens if you send photons at this thing and what happens with that. Maybe that would bring in something new, but it seems a little worrisome. I mean, in other words, this is kind of a lacuna in my understanding of decoherence, because it seems like, at least at this very first step, when I just have the baseball decohering by having the atoms of the air and light and so on scatter off of it, that doesn't localize the baseball. The eigenstates of the density matrix are just as delocalized as they were without the interaction.
So I'm a bit puzzled by your example.
Excuse me, guys. I would just like, this discussion needs to be pursued, but I would just like to officially terminate the session of Professor Don Page, and maybe we can stop the recording and give him a last round of applause.